Hello and welcome back to Lesson 2. In this part of Lesson 2, we're going to continue our revision of Newtonian fluid flows. I would like to investigate with you whether or not we can estimate the pressure drop in a simple but relevant two-dimensional geometry, a tapering tube. Tubes that taper, or decrease in radius with increasing length, are found in many kinds of polymer processing operation, for example in some extrusion dies and in calendering operations. Being able to estimate the pressure drop along these geometries is therefore a useful skill. Our approach will be to use the lubrication approximation. This makes the assumption that the flow is essentially unidirectional and solves the equations of motion accordingly, but it takes into account the changing geometry in the boundary conditions. This lesson explores how this can be done, but firstly, let's start with a bit of a recap. So, we talked in the previous part of this lesson about the Navier-Stokes equations and about Cauchy's momentum equation and about solving these equations and about how we have to make simplifications to solve the equations, because in order to make them tractable analytically, we need to typically reduce them down to a set of equations that we can deal with. I've put there on the whiteboard a reminder of the Navier-Stokes equations. Now remember, in their full-blown form, that one equation actually represents three equations. They're coupled, nonlinear, partial differential equations, and in order to solve them, we have to make some assumptions. We can solve them fully computationally, but analytically, it's somewhat more difficult. So, to start with, let's think about two fluid flow situations that you will have seen before. Flow in a Cartesian slot, and flow in a cylindrical cuvette, where you've got a stationary outer cylinder and a rotational inner cylinder. Now, you'll have solved the Navier-Stokes equations for both of these geometries. What assumption did you make? One of the key assumptions that you made was it was a one-dimensional flow, a unidirectional flow. In fact, up until this point, it is likely that you've only ever solved the Navier-Stokes equations in one dimension, which is fine. You can solve them in more than one dimension, as we will detail in this lesson and in a bit of the next part of this lesson. So, many polymer processing flows are not unidirectional. They're two-dimensional or three-dimensional. And again, sometimes we may want to get insight into the nature of these flows. But again, as I said in the last part of this lesson, always try and make sure that you know the accuracy of the answer that you're trying to solve. So, can we get away with a simple estimate of a pressure drop without having to go to some horrible numerical method in order to get a really high precision answer? So, let's see how we can start to extend our knowledge of approximations to see if we can fill that gap. Now, the lubrication approximation is a really elegant way of doing this. It's valid for mildly tapering tubes, and there I've put on the whiteboard a diagram of a mildly tapering tube. And the first step is to assume that really the dominant change in flow velocity is across the thickness of this tube, or the diameter of this tube. Of course, there's going to be some change in velocity along the length, because due to consummation of volume, if we've got an incompressible fluid, the fluid is going to be moving more slowly at P1 than it is at P0. But the magnitude of that change is small compared to the change in velocity across the width of the slot, or across the radius of the tube, because we're going at full velocity in the centre line and typically at the wall velocity, which is usually 0, at the edge. So what we're going to do is, first of all, solve our equation of motion for a one-dimensional geometry to get a volumetric flow rate. We're going to assume that these two geometries in the first step are effectively analogous. In the second step, we're going to find an equation that describes the shape variation of our tapering geometry. And in our third and final step, we're going to tie these two factors together to develop an expression that allows us to calculate pressure drop as a function of length in that taper geometry, assuming that the dominant flow can be more or less described as unidirectional. So you'll see right away there's going to be a limitation on this method as to exactly how much this tube tapers as a function of length. if it's tapering a great deal, then this may not be a very accurate way of estimating pressure drop. But if it's only tapering slightly, then it may well be fit for purpose. So let's start by listing out our assumptions and our approximations for this analysis. So there on the board, I've sketched the diagram of the flow, and you should always do this to start with. Sketch a picture of what's going on and mark on that picture a flow field and mark on that picture relevant parameters. So let's say my taper starts at a radius r1 and over a length L it linearly decreases to r0. Over that length L I've also got pressure driven flow going from P1, which is higher than P0, so my flow is going there from left to right in the diagram. Okay, so let's start to make some assumptions. I'm going to assume that my flow is steady. There's no time variation of velocity, so any derivative of velocity is 0. Furthermore, I'm going to assume that the flow is effectively non-inertial. It's creeping. There is a mild spatial acceleration in this geometry. We're going to neglect it because of the non-inertial nature of the flow. So we're looking at small Reynolds numbers. This is fine in polymer processing because don't forget most molten polymers have incredibly high shear viscosity, order of thousands of Pascal seconds. And so a Reynolds number based on a 0 shear rate viscosity is likely to be very solidly in the creeping regime. So that allows us to make this assumption in safety. Since we're creeping flow, we're already laminar, so we don't have to worry about the onset of turbulence. Since this tube is horizontal, we're also going to neglect the effect of gravity. Okay, so let's think about velocities. My velocity, I'm going to say, is along the axis of the tube, in the direction of flow, which I'm going to call the z direction. I'm furthermore going to say that that is the only velocity that's present. Yes, in reality, we've got a taper, there's going to be a slight inward flow as well, but we're neglecting that as being very, very small compared to the magnitude of the axial flow. So we're going to assume that the velocity is in the axial direction, and it only changes with radius. Again, to reiterate, we know it will change with length as well, but the change in length is very, very small compared to the flow change as a function of radius. So if we think about pressure now, we're going to assume that pressure only changes in the z direction. Same reasoning behind that as velocity only changing with radius. So we're only looking at the unidirectional flow case. Okay, in terms of geometry, we're going to assume that the flow geometry is cylindrical, and I've put some coordinate axes on there now. So my axial direction is my z direction, my radial direction is my r direction. I've got centerline symmetry, which is fantastic because that makes the problem a lot easier to solve. And furthermore, I'm assuming that there's a linear decrease in radius as a function of length along the axis. Okay, right. We're nearly there with our assumptions now, a lot of them. I'm going to assume this is pressure-driven flow. I'm going to assume that due to symmetry, that we have got 0 shear rate at the center line on that symmetry axis. That's effectively saying that's where my maximum velocity field is found, so the derivative of a maximum is 0. And if you remember, a derivative of a velocity plus its transpose is equal to shear rate. So there's no shear, hence no stress, along that symmetry axis. Furthermore, I'm going to assume both of my walls are stationary and that the no-slip boundary condition holds, so my axial velocity Vz is going to be 0 at the walls at r equals big R of z. Okay, so that's a list of assumptions and approximations. Let's now start by solving the equation of motion in one dimension to get an expression for the volumetric flow. So again, I'm going to start by drawing my diagram. There we have now just a tube of constant radius. Pressure-driven flow from left to right is cylindrical symmetry, and I've placed my axes on the center line of that tube. So I'll write down the Navier-Stokes equations, and I'll use my knowledge of the assumptions that I've made to simplify them. We said our flow is steady. We said that we're also going to ignore spatial acceleration. So all the terms on the left-hand side, rho dv by dt, are set to 0. If we look at the right-hand side, the remaining terms, because our tube is horizontal, we're neglecting gravity, so Fg falls to 0. And all we're left with is the interaction between the pressure field and the velocity field. and this is sometimes known as Stokes' law. So grad P equals mu del squared V. Now what we're going to do is to simplify this further by considering our coordinate system and by considering which parameters in pressure and which parameters in velocity actually change. We said that pressure changes along the axis in the z direction, so that's the only variation in pressure we need to worry about. And we said that we've only got a z direction velocity that dominates, and that changes with r. And so that allows us to simplify Stokes' law to this differential equation that I've just put on the board there. Okay, great. Now we can solve this, and indeed you have solved equations of this many, many times before. So we get a parabolic velocity field, as expected. We've integrated that differential equation twice. On the first integration, we make use of the boundary condition that there's no shear rate, it's no stress on the centre line. So the derivative of velocity with respect to radius is 0 when r equals 0, which gives us our first integration constant equal to 0. Now note, in this expression, dp by dz, dp by dz here is negative. Now, if we think about why that is, the pressure at P1 is greater than the pressure at P0 in order to drive flow in the direction that we want. So pressure actually reduces with increasing length along the axis. So that's a negative pressure gradient. So dp by dz is negative, so dp by dz is minus delta P upon L, where delta P is simply P1 minus P0. Okay, so what we now need to do is to get our volumetric flow rate. And hopefully what you remember from this is my volumetric flow is an integral. And what we're saying here is because I've got centerline symmetry, I can start at the center of the tube and work to the outside edge. And at an arbitrary radius between those points, little r, I can think of a perimeter of length 2 pi r. Now, if I think of a tiny little element of area that can belong to that perimeter, 2 pi r times delta r, the velocity at r flowing through that area is going to be the volumetric flow rate at that point, which will contribute a little bit to the entire volumetric flow rate. So if we think about repeating that operation over all radii from the center to the outside edge, we end up with the integral that we've written on the board, and we end up with an expression for the volumetric flow of a Newtonian fluid through a pipe. And again, you will have seen this before. Now, if any of the steps I've taken so far are unfamiliar, please go back to the previous part of this lesson, look at the videos I linked in there, and make sure you go and revise this material. Okay, so our volumetric flow rate there is a negative quantity. It's a negative quantity because we've still got partial dp by partial dz, and we said that was negative for flow in the sense that we put on the board, and so overall our volumetric flow rate will be positive. Okay, so that's step one. We've got an expression for our volumetric flow rate. Let's think about step two. Let's find an equation for the shape of the object that we're dealing with. We've got a cylindrical taper. At the start of the taper, we have a radius r1. That linearly decreases with length to a radius r0. And so this is a nice, easy shape to describe. We can say that our radius as a function of position along the tube is simply r1 minus z over L, r1 minus r0. Great. Okay. Nice, easy shape. So let's move on to step three. All we're going to do now is bring together step one and step two. So there's our diagram of our taper tube, just to keep it fresh in our minds what we're solving. Let's put our result from step one on the board. There's my volumetric flow rate. Minus pi r to the 4 over 8 mu dp by dz. Step two gave us an expression for big R as a function of z. So let's substitute that in and rearrange such that we have a differential equation that describes the variation of pressure along z. So dp by dz is now that expression there. And if we look at this carefully, z appears just once. It's in the denominator. So all we have to do is solve this differential equation to get an expression for pressure drop along this geometry. It really is as simple as that. Now, of course, we need to be a little bit careful because in the denominator, Z appears in that quartic expression. So to make life easy, I'm simply going to make a substitution. I'm going to say let that quartic bracket just equal a parameter. Let's call that parameter u. And then if I take the derivative of u with respect to z, I end up with a combination of terms involving L and R1 and R0. And I'm just going to rewrite my differential equation with that substitution. And so what I'm doing is really just integrating this. And we can see there on the right-hand side where that quartic expression involving z over L and R1 and R0 was, is now just simply u. So that's nice and easy to deal with. And in order to do that, I'm integrating now with respect to u, and I've got that factor in there that allows me to do that minus L R1 over R0 as a result of du by dz. So all we're going to do now is integrate. And what we find is, when we do that, we end up with an expression that looks a little bit like the following. We've got on the left-hand side my pressure drop. Perfect. That's what I want to find out. On the right-hand side, I have got my group of terms involving R1 and R0 and some other factors. And I'm going to substitute in the limits for R1 and R0. And what I find is the following expression. P1 minus P0 is equal to a group of terms involving viscosity and volumetric flow and length and radius. Now let's look at this a little more carefully. One of the things that I hope you always do when you do an analysis is find a way to check your answer. One way we can check the correctness of this answer is to say, well, does it reduce back to the expression for Newtonian pipe flow? So if I set R1 equals to R0 equals to R, I should get a familiar expression. However, if we do that here, if you look very closely, in the denominator we've got an R1 minus R0 term. So if we set R1 equal to R0, that becomes 0, and we get a division by 0 problem. So that expression is either wrong, or there's a trick we can play to eliminate this problem. And as it happens, it's the latter. So let me show you what we're going to do. Focus carefully on that term in square brackets, 1 over R1 cubed minus 1 over R0 cubed. I'm going to manipulate that. I'm going to cross multiply both of those together and reverse their order. Because what I want is a term in the numerator of that bracket, which is of the form R1 minus R0. Because if I have a form of that nature, I may be able to simplify it down to extract R1 minus R0 to cancel with that problematic term in the denominator. At the moment, I've got R1 cubed minus R0 cubed in the numerator. However, that difference of two cubes can be rewritten as follows. And when we do that, we end up with an R1 minus R0 term in the numerator, which cancels out the problematic R1 minus R0 in the denominator, and no longer gives us a division by 0 problem. So our rewritten expression for the pressure drop along our taper tube is there in the blue box on the whiteboard. And now we can do our cross-check. We can set R1 equals R0 equals R, and when we do, we recover the expression for the volumetric flow of fluid in a pipe, which is great because that's exactly what we should get. So let's summarize a few key points. What we've done in this part of this lesson is introduce the lubrication approximation, and that has now given us the ability to estimate pressure drop in tapered geometries, so mildly two-dimensional geometries. We've done this analysis for Newtonian fluid, and in the next lesson we'll see how this expands to analysis in a generalized Newtonian fluid. So it's got great applicability for materials that shear thin, and of course all of our polymers will shear thin. We introduced 3 steps for this analysis. First step was to solve the equation of motion for a one-dimensional geometry to get a volumetric flow rate. The second step was to find an equation that describes the shape variation of our taper. The third step was to find the pressure drop via combining those two expressions together from step 1 and step 2. And that allows us to get an expression for pressure drop as a function of length in a mildly tapering geometry. Now, I've said all along mildly, gently tapering. One of the things we need to establish is the limits of this analysis. Just how mild is mild? So that might be one of the tasks for your homework.